Assalamu alaikum everyone. Okay, so in this video we're gonna learn how we can use MATLAB to model different systems. So the first example that we're gonna see is this magnetic levitation model. Okay, so here is the state space equation that represents the mathematical model of this system. Okay, so here if you read this paper, so all these states are defined that x1 state represents, I believe, this theta, and this theta is defined as the air gap between the center of the iron ball and magnetic coil. This x2 is this rho is defined here as the momentum of the ball, and this x3 is represented using this lambda is the flux produced by the field. Okay, so similarly we have different models of different systems. Here is a model of a brain tumor cell. Okay, so there are healthy cells, there are immune cells. X3 is the immune cells, X2 is the healthy cells, X1 is for the tumor cells, X4 state is for the drug intake. Okay, so similarly here we have another paper that represents the mathematical model of a quadcopter system, which is a drone. Okay, so this X1 and X2 state represents the pitch angle motion, these represents the roll angle, and these represents the yaw angle, and so on, the x coordinate, the y coordinate, and the z coordinate. So these different equations represents different dynamics of the system. So for now let's go ahead and look into this magnetic levitation system. Okay, so this mathematical model is derived using all these uh, principles from of the physics, and finally uh, we are the results we get is this state space equation. Okay, so what we have to do is this: we have to compute the actual states. For example, I need the information of, if I go give a certain input, what would my x1 state be, what would my x2 state would be, and what would my x3 state would be. Okay, so for that what we do is that we simulate these equations and solve these differential equations using MATLAB. Okay, so let's go ahead and do that. So I'll open the MATLAB. Okay, so you go ahead and open and go to this part and click on the Simulink, open a blank model, and you'll come up here. Okay, so then what we do is, okay, so go to modeling, go to modeling settings, and or just press Control E. So go to modeling settings, and we'll just change some of the settings in the first place before we start. Okay, so we'll just make a fixed step and we'll use this discrete time. Okay, yeah. So discrete, no continuous states. Okay, and we'll just assign a fixed step size, because normally the normally available controllers in the market can go ahead and compute the equations with this sampling time. So it is better that you define a fixed rate rather than its different value at each instant. So since all simulation should be real life applicable, so we're gonna go ahead and directly use a discrete with no continuous states, and I'll just untick this and make it an array for future references, and that's it. Okay, so these are the two settings, and okay, fine. So let's go ahead and I'll just double click anywhere and I'll write MATLAB function. Okay, so here is a MATLAB function block. So I'll just rename it and I'll say, okay, it's a plant model. Fine. So I'll just click the control button and drag it here to recreate it another one. So I'll just name it the controller part. Okay, so I'll just double click first. Let's work on this plant model. So I'll double click and I need to write the equations of this system in this model. Okay, so let's go ahead and write these. Okay, so I have written these equations. So basically what I did was, uh, this is x1 dot is equals to x2 over m, x2 dot, all the this and that. So I just wrote exactly these equations and defined some variables x1 dot, x2 dot, and x3 dot. And These are the equations that originally represent the mathematical model of the of this magnetic levitation system. Okay, so all I have to do is compute the original state variables x1, x2, and x3. This is x1, this is x3, and this is the x2. So what I have at this moment is the derivative of these equations. So if I somehow compute this derivative, I can take its integral and I'll get the actual state. Because what actual state represents is, for example, here x1 represents theta. Theta was, I believe, it was the air gap between the center of the. Okay, so if I compute x1 somehow, I would know what is this distance. Okay, and that's the information that I want. So normally whatever your system is, for example, in another model of this brain tumor model, if I compute x1, I would know how many tumor cells are remaining in my body, in the patient's body. Okay, so if I compute x2, I would know exactly how many healthy cells are remaining. If I compute x3, I would understand how much immune cells are remaining. In another system, if I compute this x1 state, I would exactly know what is the roll angle, the tilted angle of my quadcopter system. So every time, for every system, all we are interested in is the original state variables, because they represent the exact information that you are normally interested in. Okay, so to compute these original variables x1, x2, x3, what we can do is we can just compute these given equations. Okay, and we can just take the integral and get the original variable. So here x2 divided by m, so this was the first equation. X2, x1 dot was x2 divided by m, and similarly so on. So I put a dot here between each operator. Okay, so that gives a scalar value. Most of the times, if there is a complex value, the error goes away. So it's always better. You can go ahead and put this dot every time you put a divide or taking a power or put a multiplication sign. Okay, so if I wanted to compute this x1 dot, what I would need is I need the information of this x2 and I need the information of this m. If I have the value of these two things, then I can easily compute this first equation. So x2 is the state variable that I can get after integrating this part. So I will just leave x1, x2, x3 as it is, and I'll concentrate on the rest of the information. So I'll just leave this x3 part, and what else is here? Okay, k. So here I had this m, in this equation I have this k, m, and g. So what I'll do is I will define these variables. So I define k is equals to 1, g is equals to 9.8, m mass of the ball in grams or kilograms. You have to look into that. What is your unit? Okay. Similarly, r, the resistance of the coil, and what else? Okay, k. K is it is also defined in the paper. What are these symbols, and what is K, what is this and that, and the values are also defined, evaluated using experimental data, and defined in the research papers. So I defined all these constants except for the actual states x1, x2, x3. So once I have all this information except for the variables, I can compute these exact variables. Okay, so x1 dot, x2 dot, and x3 dot. Okay, so this is the first command. You use this function command with square brackets, and whatever you put in here is the output that you can get from this block. For example, here you see these are those three variables. That is the output of this block. Okay, so whatever variables you put here are the outputs, and whatever variables you put here are the inputs to the block. So if you want to take data from some external point, so you can do you can define these variables like this: x1, x2, x3, and u1. Okay, so since I am getting these x1 dot, x2 dot, x3 dot, these are the derivatives of the states. What I would use is discrete time integrator, and if I do this, I'll just press the control button, drag it, press the control button, drag it, and well, what I can do is just I'm taking the integration and sending the output of this integration back to the system. So Here it was x1 dot, indicating that the derivative of x1, if I take the integration of the derivative of the x1, I would get the actual x1. So this x1 is fed back to the system. Similarly, we go ahead and do this for x2, x3, x1, x2, and x3. So that is why I said earlier that we don't need to worry about this x1, x2, x3, because we will get them like this. Okay, so there's a better way to avoid all these wires. Okay, so just type go to log. Okay, it is just like a transmitter signal. Always I use this global variable because we'll make subsystems ultimately. So I can just make it like this, make more copies. Each go to block should have an individual specific name. So x2 and x3. So what I can receive for the receiving side, I would write from block and click it like this. Okay, so this one is x1, this one is x2, and this one is x3. So this is equivalent to what I did earlier. Rather than directly connecting this wire all the way to this point, what I can do is just send the data and receive it. So these names should be equal to each other, equivalent, right? So this is a more better and sophisticated way with well, less number of wires, and so the readability can increase, but of course the function is same, so it's up to you. So we have x2, x1, x2, x3. We defined all these constants, while we have this u variable which was originally mentioned here as well. Okay, so we don't know the value of this u. So if we change the value of this u, the value of x3 dot will change. If the value of x3 dot changes, the value of x3 state will change. If the value of x3 state changes, the value of x2 dot will change. If x2 dot will change, x2's values will change, and if x2's value change, x1 dot changes, and ultimately x1 changes. So basically what we can see is that changing the value of this u directly controls or changes the value of this x3 state, and indirectly changes the value of this x2 and x1. So we have to very carefully decide what the value of this u should be, so that we are not just computing x1, x2, and x3 values, but rather we are making it equal to whatever we want. If I want x1 equals to 10, so I have to design this u in such a way that x1 should give an result near to 10 or exactly like 10. Okay, so this u part is the controller part, because changing its values will change the values of the state. So you have to design it in such a way that those those states will get a value that you want them to get. Okay, so this is the u1 part that we need to compute. So here we designed another part, the controller part. It was another MATLAB function. So we'll just go ahead and open this. And today we'll be implementing the sliding mode control, the basic sliding mode version. And we'll see how the sliding mode control will behave for this system. For now, we cannot just run this system. We can't do anything because the equations will not be computed because it is incomplete. We do not know the value of this u. Okay, and for what time it should be, we do not understand that. So our final results are these results. What are the values of this x1, x2, and x3? So what we can do is we can put a scope over here. Okay, which is the oscilloscope, right? So we can just click it here and see the value of x1 state. But first we need the value of this u1. So let's design the value for this u1 using the sliding mode control. Okay, so to design the controller or the controller, what we need to do is take a series of steps. So I'll be just taking direct steps for the implementation of sliding mode control, and I'll make a separate video regarding the sliding mode controller theory and how it works and why these steps are taken the way they are taken. So this is more of an applied SMC video. Okay. So what we need to do is step one is define the references for these states. Okay. So we have these states that we want to calculate. So these are the derivatives of these states, and these are the actual states which will give you some result, but that result is meaningless unless well, you compare it with something, right? So the aim is not only to compute the values of this theta, which was this air gap, right? So and this momentum of the ball and the magnetic flux. So the aim is not only to compute these things, but rather to make these things equivalent to something that you want. For example, if I want the distance between the ball and the electromagnet, I want their distance to be 0.1 cm. So what I would want is design u in such a way that this distance is 0.1 cms. Okay, so I don't only have to compute this x1 state. Okay, I don't have to just compute this state. I want this state to be equal to something as well. That is the ultimate aim. So similarly, I want the momentum of the ball to be something. It will be computed. All these states will be computed, but the computation should reflect to some meaning. Okay, so what we do here is we define these references. So I want my air gap, the theta, the x1 state, to be equal to the value 10. I want the momentum of the ball to be equal to value 3, and the units are defined in the research paper. And I want the flux to have the value of 1. So I define variables with the name reference, because reference is the value that you want your system to go to, right? Reference value, desired value. So there are different names, right? So I defined the references for these states. I had three states, so I defined three references. Okay, x1 reference, 2 reference, and 3 reference. This is the value that I want these states to go to. Okay, so ultimately these values will be computed, and we'll see if they did go to that point or not that we defined. For example, I will see if x1 reference is 10. So ultimately when x1 is computed, I will see if it is near 10 or how much time it took to go to 10. Okay, so the aim for this x1 is go to that x1 reference value. The aim of this x2 state is to go to that x2 reference value, and similarly for x3. All that happens by manipulating this u at every instant of time. So that's the basic concept. Okay, so well, we define the references and we define the derivatives of these references, because this will be used. Okay, so we have the reference value for the states and we have the derivative of these reference. Okay, so the derivative of 10 is 0, derivative of x2 reference is equal to 3. So the double derivative would be sorry, the single derivative would be 0, and so on. So after that, we'll be defining some error terms. So error is something that is the difference between the actual value of the state and your reference value. Okay, so ideally the error should be 0, because this actual state should be equal to the reference value, right? That's the ultimate aim. So the ultimate aim of an engineer is to make this error go to 0. Okay, so all the effort is to make these errors go to 0, because these errors are defined as such. This is the actual state and this is the reference value. So actual state should be equal to that. So we define three errors for the three corresponding states, and then what we do is that, okay, so then we define the dots of these errors, because these will be used at some point. So the dots of these errors would be x1 dot minus x1 reference dot. Okay, so we just defined this x1 reference dot. Okay, so we'll just take that variable, and where will we get this x1 dot? So we defined this x1 dot originally in the plant. So let's take these equations and we'll just put these equations, because we want to compute every equation at each part. Okay, so here it is. So we use those same equations from the model. Okay, these equations x1 dot x2 dot, we get the information from here. And so up to now what we did was we defined the references and their corresponding derivatives, the reference for the states, their derivatives, the error of the states, and their derivatives. Okay, now we go into the major role of this sliding mode control. So we define a sliding surface which is simply the sum of errors. So we had three errors, right? E1, E2, and E3. We had three errors, so we define error 1, error 2, and error 3. Okay, and we multiply some constant by these with these errors. Okay, so this will change the weightage of contribution of this error. Okay, so we can just normally put a1, a2, and a3 equal to 1, so all will have equal contributions, but these are called the tuning parameters or gains of the controller. Okay, so we use optimization algorithms, reinforcement learning, or different techniques to compute these gains, the value, the tuning parameters, because they define how much weight should be given, how much weightage should be given to this error one part, how much to error two, how much to error three to get the optimal result. So these tuning parameters play a crucial role. Okay, so you can't just ignore them. So we define the sliding surface, and then what we do is this: we will will not going to be. I'm not going to define it here, but let's go ahead and see that we will take the derivative of this s. So I would say s dot maybe. Okay. So the derivative would be equal to a1. A1 would remain as it is. A1 e1 dot. Okay, and plus a2 e2 dot and a3 e3 dot. So what we do is that we take the derivative of the sliding surface and we equate it to a reaching law of the sliding mode control. Okay, so that is minus beta the times the mode of sliding surface times the signum of sliding surface. Okay, so we can use a saturation function as well, but normally the first test can be done with the signum. So what we do is that we take the derivative of the sliding surface and we equate it to the reaching law of the sliding mode control. Why would we do that? Well, that's the theory of sliding mode control that we will cover in an extra video. Okay, so we equate these two things together and then we put the values of what is e1 dot. Okay, so what we do is we take this value and we, rather than e1 dot, we just put this value e1 dot here. Okay, and we take the value of e2 dot. So, or we can just go ahead, because since we defined it here, so we can just let this e1 dot as it is. Okay, so then here is the e2 dot. So we take the value of e2 dot and put it here, or just let it be, and then we have this e3 dot. So in this e3 dot, e3 dot is equal to what? E3 dot would be e3 dot is equals to x3 dot minus x3 reference dot underscore dot. Okay, so we know the value of this x3 reference dot, which was 0, and this x3 dot is can be taken from this point, right? So now what we do is, so we take this x3 reference dot's value. Okay, and we put it at this point. So this is our x3 dot, right? So what we do is we take this value of x3 dot, control x, and put it here. Fine. So ultimately I'll just delete this part, since because these are the steps only. Ultimately we have all of this equation. I'll just delete this x s dot. Okay, because we already know this is s dot. So we have this equation, this huge equation, where s dot is equal to this reaching law. All we have to do is this, to make this u1 a subject and put everything on the right hand side, and that's our final control law. Okay, so we did that here. So this u1, by making this u1 a subject. Okay, so this u1 appeared in this highest state, so I just deleted the rest of the steps which were not necessary. So I'll delete this as well. We understand the concept that we have to make this u1 as the subject, and let's go ahead and delete the rest. So this u1 is the final control law that we must send to the plant. Okay, so I'll just paste something here because some of these parameters were again being used here. Okay, well, at some points, yes. So M is here, G is here, K is here. So we defined these M, G, R, K again because these were being used in the controller design as well. Then we have these parts as the outputs and these parts are as the inputs. Okay, so when we defined the reaching law, which was well, what we did was we took the derivative of s dot and we equate it to minus beta abs of this sliding surface. Sorry, in the previous part, I believe I wrote this small s. It should be equal to this capital S because well, this is our sliding surface. So we take its absolute value and well, multiply it with the signum of s. So this beta is also a tuning parameter, and there is an extra part that we can do is well, take the power of this absolute sliding surface as well to well see how much weightage should be given to this sliding surface as well. Okay, and this is also the magnitude of the change of magnitude of all this equation. So here alpha b for beta, and we had this a1 a2 and a3, this one a1 a2 and a3. So all of these are tuning parameters, so we take them out, beta a1 a2 a3 and alpha. So, okay, so we must determine their best values by some method. Okay, so let's see what our controller at the moment looks like. So we have this x1 x2 x3, then we have the three states. So we can use this same variable, the information comes from the plant. Okay, so well, here's the x1, the x2 and the x3. Okay, so let's just connect these. Okay, so at the moment we do not have any value for these. We don't know what they should be. So what we'll do is, well, just give one for now, one to beta and all of the rest. So let's just give the constant value one. So I double clicked and typed constant and it was it. There it was. So, well, these are the reference values that I can go ahead and send somewhere. So I can say x1 reference, x2 reference and x3 reference because I will need to compare the values. Okay, so I will also be sending this u. You can type u or u1 or whatsoever it is. So here we'll just receive this u. So what we lacked was this u. Now we have computed this u, and we could use just directly put this wire to this part as well, but this way it is more neat and clean. So let's just go ahead and make a little separate portion for the results part as well. So okay, so what I would want is I would want to use x1 and x1 reference with this scope. So this is x1 and this is x1 reference. So I can just compare using a single scope. Okay, so I can just maybe copy paste this two times more. Okay, so I can make this x2 with the x2 reference. Okay, so I needed to rename these as well. Okay, so this is x2 reference and this is x3 reference. So x2 with x2 reference, x3 with x3 reference. So that's it. Well, we have done it. So what we can do is just select all of this and press Ctrl G to make it a block. Okay, so all of this the whole system is in there. You can just rename it, Control Shift G to undo it, and like I will press the Control G to make it a block, Control Shift G, so I can just name it plant, and this is the controller part. Okay, So similarly, I can just press Control G, Control Shift G. Maybe I can just let it be at G as well. So results part. So all is done, and now we go to this simulation point, and well, let's pin it for now. Okay. So well, 5 seconds is good enough. Let's click on this run part and see how it works. Okay, so it's running and it's done. So let's open this scope number one. Okay, so double click on this and the scope will open. Okay, so here we can see, maybe we can just run it for 10 seconds. So we see a little bit more of how the output performance was. So double click. So this blue line is the reference value. It is what it should have been. And this yellow line is the actual output. So it took about 6-7 seconds to go to very near to 10, but it did not reach 10. So there was this small steady state error. You wanted the x1 state, the air gap, to be 10, but after 6 seconds or 7 seconds, it was very near, maybe 9.3 or 9.4, but it did not reach 10. Similarly, for x2 state, what you wanted was, you wanted it to be 3, but after 7-8 seconds, it was 0. It did not go to 3, or maybe you shouldn't have asked it to be at 3. And then we have this one. Okay, so this is how you see the results. You give the input what you want this state to be, and you design a controller and you put these equations and compute and check their results and compare these results with the reference values. So here I would add a point that the values of these gains make a huge difference. With the values of this 1111, here you can see that it took about 7 to 8 seconds to reach a near value to the 10. So what we can do is use optimization algorithms and different techniques to compute the best values of these controllers, of these gains, sorry. Okay, so I did compute it using okay, so here is another model for for the brain tumor x1, x2, x3, x4. There are four states. The step one would be to create a MATLAB function block, write all of these equations, define all these constants, this k3, this n1, all this and that. Just let x1, x2, x3, x4 the original states as it is, because we'll take the integrator and get the values. So we would be left with this u part. So we'll be using sliding mode control to make this U part. We create an other, for example. So in this plant, we'll define these equations. We'll define all these controllers, and then we will be left. So we'll be using the integrator, and we'll get the actual values of the states, and we'll give them back to the system. So these will get the values. All we would be left with is this u part for this new part as well, for this new model as well, for every model. Okay, so again, for computing this U part, we'll design a controller. In the controller design, what we will do is just define the references, define their derivatives, and then define the errors, define a sliding surface, that is the sum of errors, give weightage to each error, and you will ultimately compute these values using some method, and then take the derivative of this sliding surface and equate it to this reaching law. Okay, minus beta absolute of sliding surface, which you just defined before, signum of sliding surface. So this is the reaching law. Take its derivative and equate it to this equation, and then when you open this whole equation, open this error 1, error 2, error 3, so you would have this u1 variable. Make that u1 variable the subject, and you will get the ultimate control law. Okay, so this is the sliding mode control law. This equation represents the sliding mode controller. Okay, and the rest is the procedure. then just get the values using hit and trial. You can get the values, but that's not a very good method. So similarly, for another model here, for this specific model, you take two equations at a time. So first we take these two equations and we define the plant and we'll define the constants and everything. We compute this u the same the same way, and we'll do the rest of the things, and then we can observe the results in this way. Okay, so this is how you implement a sliding mode control onto some plant. And the next we will be looking at how we can get the best values of these optimization, using some optimization algorithm for these gains. Okay. Okay, lastly, for these two equations, I have added these notes for the design process of the sliding mode control. For example, if we have these two states, okay, so the first part is to define this sliding surface, which is the sum of errors. So since there are two states, so there will be two errors. If there were three states, four states, there will be corresponding three or four errors in the sliding surface. So since this control law is associated with the two states, so we'll go ahead and define two errors, which are the x2 reference minus x2r, or x1 reference minus x1r, error 1 and error 2. And we have this corresponding gains. Previously we defined them as a1, a2. Here they are k1 and k2. So after defining this sliding surface, well, of course, by default, we have already defined the value of this x1 reference and its dot, and x2 reference and its dot, and we already should have the value of this errors and its derivative, the expression, not the value. Okay, so then what we do is we take the derivative of the sliding surface. So we take the derivative of this equation, the sliding surface. So s1 dot is the time derivative, so k1 remains as it is, x2 well, x2 dot, for x2 reference is x2 reference dot. So this x2 reference and x1 reference and their corresponding dots, well, we defined them what these references should be, and so we already know what's the derivative should be. So the value of this x1 dot and this x2 dot, this x1 dot and this x2 dot will come from the system. Okay, so we have the value of x1 dot and we have the value of this x2 dot, sorry, the expression, not the value. Okay, so what we do is we take the derivative and we equate it to this breaching law. So normally we can well, just use USMC, indicating this is the reaching law for SMC, or USW, the switching law as well, sometimes called. So rather than writing it again and again, we can just write this small abbreviation. So well, when we open these values, so K1 comes as it is, and apologies. Okay, so yeah, there we go. So K1 comes as it is, x2 dot well, will be replaced with the equation of x2 dot, which is this one, all of this. Okay, so this equation is replaced using this. X2 reference dot comes as it is. Then we have this plus k2 times x1 dot is replaced with the equation x, which is equal to x2. So we're, instead of this x1 dot, we write this x2, and then we have this x1 reference dot as it is. Okay, so that is equal to all of this. So instead of all of this, this reaching law, we're just writing u switching. Okay, so in the end we'll just replace it with this expression. So now in this whole equation, okay, this bottom equation, what we have to do is make this u2 a subject and everything else on the right hand side. So these are the steps of doing that. Okay, so doing this and this and this. So ultimately, this is the, apologies again. So ultimately we come up to this u2 is equals to all of this. Okay, so this is the sliding mode control law for the pitch angle control, because these two equations are representing the pitch angle. Okay, so this is a summarized process for how to design the sliding mode control, and the main crux and the main steps, and we already saw that how it would be implemented in MATLAB. So that's it. Allah Hafiz. Take care.